Hi. So I'm a horny-handed soil trade here. So Robin asked me to say something about big data because I guess it's something that's what people are thinking about these days. I'm somebody who helps you into mathematics. I'm just going to make a few. It's really my experience of big data. Yeah, I'm not going to try and draw any conclusions from it, but maybe we can have a bit of discussion. I don't think it should take too long. I've just got a very small presentation. So this is from a recent McKinsey report on big data. So McKinsey have been pushing big data for quite some time. They're very interested in big data. But I think that the nice thing about this, so this is big data in health, which is something that I'm thinking about quite a bit. If you look along the top, I think that points out the issue, or it summarises the issue around big data very nicely. So interlinked data inputs. So if you like, you can put big question marks over each of these things, and I think those particular areas and their relationship is kind of absolutely very fertile ground for studies of science. So you have this issue about what the input is. So you have these interlinked data inputs in here around patient stuff. You've got universal IDs, patient demographics, physicians, treatment data, diagnosis, procedures, drugs and doses. This is all quite institutional data sources. This is cost data. I mean, this is an American perspective and so on. There's a whole load of stuff down here, because certainly NHS 24 in Scotland is saying that data will come from your smart TV about your behaviour. Your smart meter will be feeding stuff back. Your mobile phone will be feeding back accelerometer data, for example, recording your activity. You'll be self-monitoring with a variety of things you can attach to your phone, or will be Bluetooth devices. So there's a whole stream of stuff underneath there in terms of what the interlinked data sets are. And of course there are real problems around time and space, around how you register that data, how it corresponds to one another. There's a whole slew of stuff that's bread and butter actually in terms of understanding the way that data is together. The next, and I mean, critical thing, the thing that isn't always obvious to people, is that actually none of this makes any sense unless you have an analytical model, because you don't know why you're gathering data unless you have a model. And this has been very clear right from the very beginning, and we've got quite a long history of this in Edinburgh in terms of looking at this sort of thing, because we hosted the Science Centre here for, 10 years or something like that. And if you look at it, then one of the big issues around the complexity of trying to do e-science, trying to do, say, genomics, or, I mean, if you look at it, anything other than physics, anything other than high-energy physics, where there is one model, I mean, just fairly recently, that might open up again, but they're fairly confident that there is only one model at the moment that they're really interested in. But if you look at all of the rest, then the thing is you have scientific data, and then you have huge array of models. So for example, if you look at astronomical data, then the problem is that really, as an astronomer, what I want to do is I want to query the data according to a model. So in other words, really what I want to do is I want to say, okay, I have a model of where the lost matter is in the universe, so it's small brown dwarfs or something like that. And I want to look at the observing data not with some high energy phenomenon eyes on. I want to look at it with a small brown dwarf set of glasses on. And in order to get decent results, you need an analytical model. The analytical model is what actually acts as your filter. We'll come back and talk a bit more. And then finally, once you've got the analytical model, then you have to look and see what you're going to do in terms of decision support. And if you look along the top, this thing is disease management. So, and really none of these, I mean, so along the top is a disease management row. really none of these is particularly unproblematic, because disease management, well, what constitutes a disease? Yeah, we know from Bowker and Starr, for example, that the International Classification of Diseases is something that's phenomenally contested. It's very accurate when it comes to Western diseases, very inaccurate when it comes to tropical diseases and diseases that are suffered by people who are poor. The other thing is it's undergoing a massive amount of recalibration at the moment, because people have discovered the genome. Yeah, so many things that people thought were the same phenomenon are now different phenomena, and many things that people thought were different phenomena are now the same. So there's no stability around exactly what the disease is. The other thing is there's very little stability around what the delivery mechanism is in terms of treatment, and what we see is a complex situation where actually the capacity to understand the disease, at least in the health system, is only the capacity that you have to treat it. Yeah? So there may be lots of nice treatments around there, but actually you've got a very complex multi-dimensional space where you have to think about what the risk is, you have to think about what the stratification is for that risk, and then you're confronted with, how do I treat it? So, and what we know now is, and even down to the modality of treatment, so now we know that everybody wants to keep people out of hospital because it's too expensive, and they're much more likely to get an opportunistic infection. So actually, really ideally, I want to virtualize this. So here this is looking at predicting hospitalization risk. And then the decision support tools are, well, what is the patient risk score? And that, again, is very much on historical data, which may not be related to your population, so there's some quite difficult problems. And actually, just exactly what your workflows are and what you're actually doing as compared with what you think you're doing. Yeah, so there are, again, issues here. And then the idea is reduce spending on patients with chronic disease. So the outcome is supposed to be that you actually more effectively manage. I'll come back and talk a little bit about that in the context of Scotland. I'm sorry, I ran out of bandwidth at one point. Something terrible happened. I meant to have more images. Anyway. So I think there's a big issue at the beginning, which is the solution, if you like. The big data mantra is instead of thinking about things discretely, then answers to questions of distributions. Yeah? So actually, when I say, would you answer yes or would you answer no, it's not really a Gardner thing that puts a cross in it by two tables. It's rather there's a distribution as to whether you're likely to say yes or no, depending on what population you have to say. And so we replace yes, no's with distributions. So here's the probability that you say yes, the probability that you say no, and it's got particular distributional characteristics. And what that does is it just pushes the problem back onto what the population is. And I think things aren't problematic under two circumstances, two immediately obvious circumstances. One is if you're locked in and the context is extremely clear. So one of them is if you're on the New Jersey Turnpike and you're doing 2 miles an hour, then actually Google know you're, and you've got Google traffic turned on. And then Google know you're on the New Jersey Turnpike and they know you're traveling at 2 miles an hour because they've got a GPS satellite telling them what your position is. And in that context, you can get really accurate estimates as to how long it's going to take you to arrive at your destination. So in that situation, it's fine. Yeah? Things are, you can pretty much, provided the context is very strong, you can get this kind of result. If you look in other situations where actually there isn't enough money in it. So you look at the DARPA Network Challenge, for example. So this was a strange thing where the Defence Advanced Research Projects Agency decided it had this challenge where what it did was release 10 weather balloons across the US. And you had, using only people, only the population and the internet, you had to discover the positions of those 10 weather balloons. Now, Sandy Pentland at MIT recruited 4,000 volunteers pretty much in a day or two, yeah, who were observers all around the UK. he had a particular incentive scheme that I'm not going to describe at the moment to incentivize them to do that. And they looked for these weather balloons, and they found, I think they detected them within 8 or 9 hours. It was a very, very fast job. So they identified all, the prize was 40K. So it was $40,000. That $40,000 had been salami sliced into tiny portions, yeah, in order to get this number of people to volunteer. Because if you discovered a red balloon, I think you got something like $200, yeah. And if you recommended the person who found it, you got $100. And if you recommended the person, you got $50, and so on. Yeah. So it was a big incentive. But yeah, and they had a winner, and this was where they were released. Yeah, it was just all around the edges, really. Yeah. But suppose the prize was $1 million. Suppose it was $1 million. Then what's the incentive for somebody to interfere with that? What's the incentive to actually disturb the statistics? And there's a huge incentive for that. And $1 million, of course, is very small by comparison with what people are prepared to do in markets, for example. We have these massive leverage deals that involve trillions of dollars. So basically, things seem quite stable provided you have these kind of locked-in contexts, or you have, there's not really a big incentive for anybody to try and disturb the results. But when you move out of those two relatively narrow contexts, then what you end up with is you end up seeing the possibility for all kinds of contesting what the observations are and what the population is. And I think that around that, there's some very interesting stuff about saying, well, these things might work all very, very well, provided people are benevolent and provided people aren't prepared to gain it to their advantage, and there isn't an incentive to do that sort of thing. But actually, most people, when they're talking about how they're going to apply big data, are actually talking about applying it in situations where it actually does benefit the I'm just going to talk about a few examples. There's lots of, this is a contrast between relatively kind of well-off, well-structured medical condition and chronic obstructive pulmonary disease, which is a disease that affects poor people mostly because it's from smoking and generally not in half years. And there's this nice system called renal patient views. 20,000 renal patients are signed up. There's a large number of rare conditions associated with renal failure. There's a thing called Alport's disease that there are only maybe 1,000 people in the UK suffering from. And what happens here is it's nicely gated by the profession. So each of the consultants in the UK have kind of taken on a small group of the conditions that they're interested in. So one of the local guys in Edinburgh is an Alport specialist, which causes renal failure in early age, actually, teens and 20s. And for him, he's got a phenomenal lens through this, because actually what he's got is he's got nearly the whole population of Alport in the UK, which allows him to do really quite significant scientific work very rapidly, because all of these people are motivated to support the research. So actually what he's able to do is he's able to drill down right in, deep down into the long tail of rare diseases and get a very accurate fix on it. Because the incentive structure is right and he's gated it. Because actually membership of renal patient view is gated by clinician. Clinician will invite you in. And then once you're in there, then the individual specialists get their hooks on you and you form these nice populations. And then what they've got is they've got a very focused thing where actually they can identify the signal from the noise very clearly in the condition. If you look at chronic obstructive pulmonary disease, which is bronchitis, a whole range of associated symptoms, not really a disease, there isn't a state risk stratification for it because people haven't really done research on it. It's very difficult to identify. There's a lot of self-reporting, there's a big spectrum of conditions, and there's high variability in how the measures relate to how sick or well you feel. And this, economically, far more important condition than you. But actually, it's extremely difficult to see exactly what to do in terms of big data and these sorts of things. Because there is potentially quite a lot of data of self-reporting, and there is the possibility to train people to do things to mean that they don't get serious exacerbations. But still, it's a big problem. So there's those kind of contrasts, I think, are interesting. So I'm just running through and kind of throwing out some things that I've experienced. This is something that struck me when Donald was talking about this thing about inversion between data and context. Because we've done a couple of things recently. One where we looked at mammographic screening training, and how it is that you can get service data to become training data, and whether that's possible. And the thing that did was it really focused on moving from the data to the context, because you discovered that in the data there are all kinds of traces of the context practice that actually were quite important to some extent in terms of looking at the training context. You moving things from people actually doing breast screening to training to do breast screening. And actually, even in that relatively small movement, you got very strong flip in terms of where the focus lay. And you flipped from looking at the data, from looking at the images, rather to looking at the context of production of the images. And most of those things you don't gather. Actually, you discover that in there, when you start to look at the context, and you start to say, okay, I'm going to take this data and I'm going to move it and make use of it somewhere else, then you start to see all kinds of questions arising about how you pick the data up, how it was produced, and the means of its production. That comes up even more clearly in chronic obstructive pulmonary disease monitoring, because if you look at self-monitoring, which is what lots of people are doing, and saying that's going to be the future, so people will be taking their respiration, their heart rates, their blood pressure, and so on, and feeding it back to doctors, then the problem that we see is actually you don't monitor the context, so you don't know what the patient is doing. You end up with these decontextualized things, and it's extremely difficult to work out what's going on, because you have who's doing the work, what the environment is when they were doing it, what the history of the patient is, and it's problematic in terms of getting in a reasonable implementation of telemonitoring and these sorts of things, because at least with the systems as they stand at the moment, because they neglect really to take into account context adequately, you end up with so many red flags that the doctors don't want to use it, because all it does is increase their work. You have in the trials, you had doctors coming in over the weekend to try and clear their red flags, typically, and there wasn't really a good way of working out how to fix them. I'm going to skip this. This is something, I wanted just to say something quickly about models. I mean, you know model risk exists, yeah, but this actually relates back to what Donald, well, I think somebody raised, Trevor, you raised the thing about flash crash, didn't you? So I'll give you this is about stock pricing. So it's about the fact that, I mean, Donald mentioned that Accenture was selling at 1 cent, yeah? And Sotheby's, I think, was priced at $99,990.99. Those are actually the top and bottom limit of the system. Yeah? And practically speaking, for me as a computer scientist, why is it 1 cent? Yeah? Because if I tried to work out, if it was charged 0, and I tried to work out how many shares I could buy for $1, I'd get a divide by 0 error and the whole thing would fall over. Yeah? So actually, this here is entirely contingent on simplifying the problem for the guy who implemented this particular system. However, that impinges on the model, and there is model risk associated with this, and it's not a simple thing. So it's just one observation in a whole range of things around when you take a model, and you take a model which already makes many assumptions, so already it has lots of assumptions, and in particular the fundamental model, the fundamental problem here is that the market would always be liquid, so the assumption is there always would be liquidity, so it always would be possible to price something. But when the market becomes illiquid, then you hit the stops. And the stops are put there by computer scientists. They're put there by somebody who did the implementation. I mean, it could be different. Commonly it is. So there's this complex issue about both how models are produced by a process of negotiation of a variety of different expertises, but then they're implemented. I mean, in big data, they're actually sitting there and they're making decisions. They're making decisions about how you drive down the road. They're making decisions about which specialism you see when you go to hospital. They're making decisions about how much something's going to be priced. And that the material conditions of their production actually affects very strongly what the final outcome is in terms of things. I'm pretty much run out of time, but Gianmarco said lots of things about this. This is I think visualization is, because this is really around decision support. This is a particularly lovely and very, very rich model that nobody in their right mind would ever use in the context. It's definitely not a supervising model. This is this one about life expectancy versus fertility rates in various regions. You can beautifully see AIDS hitting Africa as you move through time. You can go from 1965 to 2009, and you actually see fertility rates declining in populations and life expectancy going backwards in sub-Saharan African countries. And you can see all kinds of interesting things around these visualizations. However, they generally have a particular set of lenses on, and I think the whole area of looking at visualization and looking at how the visualization infrastructure that we have, because there's a whole range of visualization infrastructure in place in science, in finance, and other places. And I think that the visualization infrastructure is very critical. This is the last content slide. This is the way the computer scientists are going. I'm actually working on a couple of projects like this. So the way people are pushing now is they want to see social computation. So they want to use heterogeneous populations to undertake computing tasks, stratify by expertise, accuracy, and so on, use incentives to shape population response. So if you look at chronic obstructive pulmonary disease, for example, then the solution is to, or one of the proposed solutions is to use computer-mediated social sense-making, where actually you have the social group surrounding the patient curating the time series data and trying to reintroduce and recontextualize the information. There are, of course, legion of problems around this, yeah? But I think that's certainly the way that it's going. So what you have at the moment is you have big data is data plus models, and if you like, the repair is going to be a situation where you add more people into the model themselves, and those people are going to be people who are around in context who try to recontextualize that. So here's the summary. It's sensitive to issues of population, both accidental and deliberate. Data interpretation not particularly stable, even in similar contexts. An experiment I didn't mention was something where we looked at joining up 3 databases in a NHS environment. It was specifically looking at projects, and in that there were 3 uses. There were 3 occurrences of start date across the 3 databases for projects. Each of them had a different interpretation, which means the dates wouldn't agree. So actually, if you went down, even something as simple as the start date of the project was something that was not agreed upon amongst 3 different groups who worked very closely together, and each of them maintained their separate things. So when you look at the stability of interpretation across contexts, even the simplest things is very good. Context is defined by the data, and it's usually unrecorded. So in the sense, what context is what the data isn't. Data is only comprehensible via a model, and visualization choice is strongly biased decision making. So that's my summary of big data. Thank you very much.